Okay, welcome to the problem solving portion of the video. This is for topics 1.3 and 1.4. We're going to be going over some example problems of mass percentages and empirical formulas, determining empirical formulas. So I have two example problems. The first one is just a simple mass percentages calculation. This one's going to be fairly straightforward, pretty easy. And the second one is, like I mentioned before, determining an empirical formula given some data. Okay, this one's going to be a little bit more, I wouldn't say tougher, but just a little bit more involved. Okay, so let's get started on the first one. Go over here to my document camera. You are definitely going to need your periodic table with you whenever you are doing these types of problems. Okay, so make sure you have that with you. I guess not necessarily right now, but you probably should, so you can follow along with me on there as I reference different elements. And then if you also want to do the calculations at home just to make sure that I don't mess anything up, then it's also probably a decent idea that you have a calculator with you right now so you can check my work. Okay? So, let me go back and show you that problem one more time. We need to calculate the percent composition by mass of C3H6O, which is propanone or acetone, aka fingernail polish remover. Okay? Excuse me. So, that's all that we have to start. So let's go ahead and write this down. C3H6O. Okay, now if you recall from the notes video, what I said we are going to do is we are going to assume that we have 1 mole of this substance, 1 mole of acetone. And what we need to do is we need to compare how much does 3 atoms of carbon, let me rephrase that. So if we have 1 mole of this substance, right, we need to figure out the overall mass of 1 mole of this substance. Then what we need to do is we need to say, okay, in 1 mole of this substance, how much does the carbon weigh? Compare that to the overall mass, and that'll be our percentage. How much does the hydrogen weigh? Compare that to the overall mass. That'll be our percentage for hydrogen. And then how much does the oxygen weigh? Compare that to the overall mass of the compound. That's going to be the percentage for oxygen. Okay? So each time it does ask us to calculate the percent composition. If you have 3 elements here, we're going to be looking for 3 answers. Okay? All right. So like I said, the first thing we need to do is we need to assume that we have 1 mole of this substance. And we need to figure out how much that 1 mole weighs. Okay? So we need the molar mass of acetone. Okay? And that is where you're going to need your periodic table. All right? So I'm going to sort of prop mine up in front of me. All right, so it's going to be 3 times the atomic mass of carbon, 12.01. 6 times the atomic mass for hydrogen, 1.008. And then just 1 times the atomic mass for oxygen, 16.00. Figure out what those are, add them together, and that's going to be my atomic mass for acetone as a whole. So, get my calculator up here for you guys. So 3 times 12.01 is 36.03. 6 times 1.008 is 6.048. And, well, I don't really need to do any sort of math here because it's just 1 times 16.00. Okay, then I need to add those up. 36.03 plus 6.048 plus 16.00. Okay, looks like a reasonable number. 58.078. Now, if we are trying to be very careful with our significant digits, we should only have 4 significant figures here. Okay, so I'm going to round that 7 up Okay, so the number that I'm actually going to use here is 58.08. Okay, and this is grams per mole. All right, and because we have 1 mole of this substance, right, we're assuming that we have 1 mole of this substance, that means that we have 58.08 grams of ethanol, or sorry, acetone. Okay, all right, so that's the first big thing that we need. Now what we need to do is we need to compare the masses of the carbon, hydrogen, and oxygen separately to the overall mass of this compound. Okay? All right, so if I have, all right, and guys, I'm going to go through all of the nitty-gritty dimensional analysis here, okay, because I really want you guys to see how, if you are being very careful with your units, these types of problems don't have to be as confusing as they might seem at first glance. Okay, so if we have, okay, so this is going to be for carbon. Okay, if we have 1 mole of C3H6O, I can multiply that by a conversion factor that will tell me how many moles of carbon I have. Okay, so check this out. Here's my unit, right? Mole of C3H6O. So let me put that in the denominator to cancel it out. And I want to know how many moles of carbon I have. So moles of carbon. All right, this isn't hard, right? How many moles of carbon are there per mole of C3H6O? It's really simple, right? There's 3 moles of carbon per 1 mole of C3H6O, right? That's because it's C3, right? So this is not supposed to be something super tricky, okay? This is just to show you that, truthfully, you can use dimensional analysis throughout all of these problems to avoid from getting yourself confused, okay? And I know at first glance it might actually just seem more confusing having to go through all of this, but trust me, okay? If you can be a good chemist, okay, and use your units, learn how to use your units, it really is going to pay off in the long run, okay? So that is going to be something that I continue to focus on over and over and over again throughout this first semester, because those of you that do get good with keeping track of your units, using your units, you all are going to be the ones that find yourself having an easier time as we get into the really difficult stuff towards the end of the semester and in next semester, okay? So here I have 3 moles of carbon, or well, yeah, 1 times 3 divided by 1. So I'm in moles of carbon. What I need to know now, right, if I want to calculate the mass percent of carbon, is how much does that carbon weigh, okay? And that is where, once again, the periodic table gives me the atomic mass of carbon. It is, right, if I'm paying attention to the units here, moles of carbon on the bottom, grams of carbon in the numerator, 12.01 grams of carbon per mole of carbon. Okay, moles of carbon is going to go away. This right here is ultimately just going to be 3 times 12.01, which is 36.03 grams of carbon. Okay, what this calculation says is in 1 mole of C3H6O, there is 36.03 grams of carbon. Okay, so the mass percent of carbon is just the ratio or the proportion of this mass of carbon in proportion to the overall mass of the compound. It's just division. 36.03 over 58.08. Now, these units don't cancel, and that's okay. We're calling this the mass percent, okay? So that's what this unit is, okay? I'm not going to repeat and keep writing this unit over and over again, but grams C per grams of acetone is the mass percent of C, okay? So I'm not going to write these units again. They don't cancel out, like I said, but they are still there. This is 36.03 divided by 58.08. Okay, and then we're doing a percent, right? So let me go ahead and multiply by 100 to get the actual percentage. Okay, 62.04. All right. Percent. All right, and I guess I could say percent C. So there really should be a times 100% in here. I just omitted that, but yeah, anytime you're doing a percentage, right, you have to multiply by 100% there when you do the ratio or the division. Okay, so it's quite literally the exact same process for hydrogen and oxygen. The only difference is going to be here, okay, and here. All right. For hydrogen, instead of it being 3 to 1, it's going to be 6 to 1, right? And for hydrogen, instead of it being 12.01 grams per mole, it is 1.008 grams per mole, right? Then you will get a different number for grams of hydrogen. Do your division here, right? And you'll get a different percentage. And then it's the exact same thing for oxygen as well, right? This is going to just be 1 mole of oxygen per 1 mole of acetone, and then the molar mass would be 16.00 grams of oxygen per 1 mole of oxygen. All right, and then you'll just replace whatever number you get for that here, and you can get your third percentage. I'm not going to go through all of that because this next problem is going to take me some time, so I don't want to I don't want to make like a 35-minute video again if I can avoid it. So I'm going to let you guys practice that second part, the hydrogen and oxygen, on your own. Go ahead and do that. Just at the end, make sure that all 3 of your percentages, when you add them up, that you get a number that is very, very close to 100%, right? 99.99 is okay, 100.01 is okay, but if it's much more off than that, then you must have done something wrong, okay? All right, let me go back to the slides. I will show you guys the next problem. We'll talk about it and then we'll go ahead and solve it. All right, we need to determine the empirical and molecular formulas for a compound that gives the following percentages on analysis in mass percents. Okay, so we have some mass percentages. All right, so say you just calculated these, for example. We have some mass percentages. The problem is we don't know what the empirical or molecular formula is for the compound, and we want to know what that is. Okay, so this really is kind of like a real-life chemistry example where you might be in a lab, you've created some compound, you've been able to figure out the mass percentages through some analysis, but you don't know what the actual formula is. Okay, the only other piece of information you do know is listed there at the bottom. The molar mass of the compound is known to be 98.96 grams per mole. Okay, so let's go ahead and transition over to the document camera once more. Okay, so let me rewrite those percentages. It is 71.65% chlorine. By the way, this is how I always write chlorine, capital C, and then a lowercase cursive L. That can be beneficial sometimes. Second percentage, 24.27% C. Okay, that's a 27 there. And then the third percentage, 4.07% hydrogen. Okay. You may have noticed, okay, if you're paying close attention at home, that these percentages actually do not add up to 100%. It is, I believe, 99.99%. Okay, and like I said before, that is good enough. Okay, as long as we're not super far off, then we should be okay. All right, and then the other piece of information we know is that the molar mass of this compound is 98.96 grams per mole. Okay, so we have to determine the empirical formula and the molecular formula. All right, I didn't talk about how to do the determining of the empirical formula in the notes video. Okay, so this is going to be completely new. It's actually not that bad. It is a little bit involved, but it's not terrible. So if you have mass percentages, that's actually all you need in order to determine the empirical formula. Okay, and remember, the empirical formula only tells us the smallest whole number ratio of elements in the compound. Okay, so here's how it works. We are going to assume that we have 100 grams of the compound. Okay, so think of that as like step one, right? We're going to assume that we have 100 grams of our compound. Okay, what that means then is that we have 71.65 grams of Cl, right? Because these are mass percentages. It also means that we have 24.27 grams of carbon, and it means that we have 4.07 grams of hydrogen. Okay, you technically could assume that you have more than 100 grams, like you could do 200 grams, 300 grams, but because this is based off of 100%, if we just assume that we have 100 grams, then these numbers just directly translate and we don't have to do any extra work. Okay, so it's kind of similar to in the previous problem how we'd assumed that we had 1 mole. It's kind of the same situation there. Okay, so these are our amounts of our different elements. What we are going to do now is we are going to calculate, or we're going to look at, what is the mole ratio between these three elements. Okay, not the mass ratio. We already know what the mass ratio is, right? It's 71.65 to 24.27 to 4.07. That's the mass ratio. The empirical formula tells us the mole ratio, or the number ratio, between each element, right? So like in the notes video, I talked about glucose, right? And the empirical formula for glucose was CH2O. It told us that it was a 1 to 2 to 1 ratio, right? That's the same type of information that we want here, right? But this is in masses, okay? So in order to figure things out in terms of the mole, or the number of each constituent, I need to turn these mass numbers into mole values, okay? And we can do that using the atomic mass, or the molar mass, from the periodic table, okay? So for the first one here, okay, for chlorine, I'm going to take my 71.65 grams, and in order to turn this into moles, what would need to go here in the denominator? Okay, think about that for a second on your own. What unit would need to go there? Hopefully you're thinking grams, okay? And then if I want moles of chlorine, what would have to go here on the numerator? Hopefully you're thinking moles of chlorine. Okay, so you see how some of the stuff, well, a lot of the stuff from the first topic is sort of showing up here again. That's why it's very important to stay on top of things in this course. So we have moles per gram. Okay, remember that whenever you have a molar mass or an atomic mass, the number actually goes with the grams, right? It's how much does that substance weigh per 1 mole. So if I check on the periodic table, this is 35.45 grams of chlorine per 1 mole. Okay, grams of chlorine cancels. This is going to give me 71.65 divided by 35.45. Okay, 2.02. Okay. And actually, let me show you that one more time. We start with 4 significant figures here, so let's go one more. 2.021. Okay, and that's moles of chlorine. Okay, we're going to do the same thing for each of our next elements. Okay, so 24.27 grams of carbon. Essentially what we're doing here is we're dividing by the molar mass of carbon, okay, which is 12.01 grams of carbon cancels. Okay, you can see 24 divided by 12, probably going to be pretty close to that. 24.27 divided by 12.01. Okay, what do we got here? 2.02 2.27. That seems a bit bigger than I was expecting. I want to make sure I haven't done anything silly here. Let's just run with it. 2.271. I really feel like I've done something wrong here. See, these numbers should be relatively close to whole numbers, and so I'm already kind of second guessing myself here. So give me just a moment to check on something. Did I do that calculation wrong? I don't think so. Right? Check again. 24.27 divided by 12.01. Oh, I did do something wrong. Okay, well I don't know what it was that I did wrong, but I did something wrong. So this is not this. This is 2.021. Okay, so it actually is exactly what I was hoping. 2.021 moles of carbon. Those of you that are watching at home, tell me what I did wrong. Okay, so next time we get together, if you've watched this video in its entirety, you saw me punch that into the calculator before, see if you can tell me what I did wrong there, because I'm curious. I don't have the calculator stuff available anymore. So, okay, and then we're going to do the final part here with hydrogen. We have 4.07 grams of hydrogen. How many moles of hydrogen is that? Well, once again, I'm just going to be dividing by the molar mass of hydrogen, 1.008 in the denominator, 1 in the numerator. Okay. You can see that's probably going to be about 4. Let's figure out what it is exactly. Okay, 4.04. All right, because we have 3 significant figures there. All right, 4.04 moles. Okay. Now, if we take a look up here, right, this right here was the lowest whole number ratio of elements in glucose, right? 1 to 2 to 1. Based on this information, what do you think is the lowest whole number ratio of these elements? Right? Is it 2 to 2 to 4? No, right? Because you can divide each of these by 2, right? And you arrive with 1 to 1 to 2, right? Now there is an actual way to like confirm that, all right? What you can do is you can take the smallest of any of these 3 numbers, okay? These happen to be tied for the smallest, okay? And divide all 3 numbers by the smallest of the 3, okay? So if I do that, all right, divide each number by 2.021, here's what I get. 1, 1, and this is going to be basically 2. Okay? These are the smallest whole number ratios, all right, based on these mass percentages. Okay? This is your empirical formula. Okay? So the empirical formula is, okay, so for chlorine, we have 1. For carbon, we have 1. And for hydrogen, we have 2. Okay, you could maybe rearrange this to be a little bit prettier, right? Carbon usually comes first, then hydrogen, and then chlorine. Okay, but that's not super important. Okay, either of these is technically correct. Okay, all right. Let me go to a new page. I will transfer over that empirical formula, okay, CH2Cl. Last part of the problem is to determine the molecular formula. Okay, so let me show you the slides one last time. So determine the empirical formula and molecular formula for a compound that has this information, okay? And once again, they did give us that molar mass, right, which was 98.96 grams per mole. Okay, now this part I actually did talk about in the notes video. Okay, if you have an empirical formula and you have a molar mass, you can use these both together to come up with the overall chemical formula for the compound. What you have to do is you have to calculate the molar mass for the empirical formula unit and then divide the big overall molar mass by that smaller empirical formula molar mass. That will tell you how many empirical formula units there are in the overall chemical formula. Okay, so this is going to be 1 times 12.01, this is for carbon, 2 times 1.008, that's for hydrogen, and then 1 times 35.45, that's for chlorine. Let's add those up. 12.01 plus 2.016. Oh no. Oh good, good. I thought I was not recording the document camera. That would have been bad. All right, and then plus 35.45. Okay, there we go. 49.48, right? Significant figures there. That's in grams per mole. Okay, if we take our large molar mass and divide it by the molar mass of the formula unit, we get, check this out, this is going to be nice and satisfying, 98.96 divided by 49.48, the number 2. That means there are 2 of this empirical formula in the molecular formula that has this molar mass. Okay? So essentially all we need to do is take the empirical formula, multiply it by 2, and that'll give us the chemical formula. So C2H4Cl2. Okay? So you're going to be asked to do similar types of problems in the problem set for these 2 topics. There is 1 or 2 problems at the very end of those of that problem set that are even harder than this, and I will talk about those in class on Friday. Okay. All right. That's going to do it for the video today. Please let me know if you have any questions about this the next time I see you. Okay. Thanks.